Welcome to the second lesson in the Sandhill Soaring Glider Ground School. This lesson is about gliders and glider controls. So if you've already started your flight training, then you're going to be familiar with a lot of the stuff that's in this lesson because most of the things I'm going to talk about are on our training gliders. But there's going to be a few things that are different that are available on other gliders that we'll talk about in this lesson that you might not know from our training gliders at the club. So we're going to start with talking about the wings and the horizontal stabilizers, then talk about the definitions of the different glider axes. That's going to be, we're going to refer to those axes quite a bit in future lessons, so you have to know which one I'm talking about when I use those words. Then the primary control surfaces, the elevator, the aileron, and the rudder. And talk about what makes a glider turn, so you understand the physics of what's going on. Then some of the special wing modifications like the spoilers, air brakes, and flaps, the trim system, landing gear and brakes, tow hooks, and finally engines. So this picture shows you with the what parts are on gliders. Let's start with the lifting surfaces. So the wings and the tail are designed to produce forces that are perpendicular to the direction that we're moving. We'll discuss a lot more in lesson 3 about how those forces get generated. The horizontal stabilizer actually produces a force in the opposite direction, downward force, and that makes the glider stable. We'll discuss stability a lot in lesson 5. Now, something that's quite different about glider wings compared to airplane wings is that glider wings are designed to be removable so that the glider can be transported around in a trailer when necessary. And it's common for pilots to put the wings on and off of a glider, whereas with regular airplanes, that's something that only a mechanic would do. So there are 3 different axes in that we refer to with gliders. Each one is associated with a different type of control. Pitch refers to rotation about the lateral axis. So the lateral axis goes from wingtip to wingtip, and pitch control is about the nose going up or down relative to the horizon. Roll refers to rotation about the longitudinal axis. So that refers to the wings being angle relative to the horizon. Yaw refers to rotation about the vertical axis. So there's a number of forces that act on a glider during flight. One of those forces is lift. That's the force that's produced by the wings. That's what keeps the glider from being a projectile. Drag is an aerodynamic force that is parallel to the direction of motion. Weight is the force due to gravity. That always acts directly down, even if the flight path isn't horizontal. And then thrust is the forward force. It's produced either by an engine or by a tow rope in the case of gliders. We have three primary control surfaces. The first of those is the elevator. The elevator controls the pitch attitude, the nose up, the nose down. We activate the elevators by pulling the stick back or pushing it forward, which deflects the elevator is located on the trailing surface of the horizontal stabilizer. Pitch attitude is what controls the airspeed when we are not on tow. When we are on tow, then our airspeed is controlled by the tow plane's speed, and pitch helps us control our position up and down relative to the tow plane. Second primary control surface is the ailerons. The ailerons, there are two of them, one located on the left wing, one on the right wing, generally out near the wingtips. They deflect in opposite directions. So we use them to control our bank angle, which the reason we want to bank is usually to cause turning. So they're activated by moving the stick to the right or to the left. And when you do that, when you move the stick to the right, this is a view from behind the glider, the aileron on the right wing deflects upward, which decreases the lift on that wing. The aileron on the left wing deflects downward, increasing that lift, which causes the aircraft to roll. So lift is the thing we're trying to change with the ailerons. We also tend to change the drag on the wings. When we increase the lift, we also tend to increase the drag on this wing. We intend to decrease the drag on the right wing. That causes some yaw to happen. So the primary effect of the ailerons is roll, but there's a secondary effect of yaw. We refer to that yaw as adverse yaw because it's in the opposite direction of what we would like the aircraft to be yawing. When we're rolling to the right, we're generally doing it because we intend to turn to the right, but the yaw that happens tends to point our nose more towards the left. Which brings us to our third primary control surface, the rudder, which is for the purpose of controlling yaw. So we control the rudder by pushing on pedals. When we push forward on the right rudder pedal, the rudder, which is at the trailing edge of the vertical stabilizer, it deflects off to the right and it pushes the tail to the left so that the aircraft rotates in a yaw direction. Most of the time, our goal is to keep the glider pointed in the same direction that it's moving. That's called coordinated flight. There are some exceptions to that, which you will learn about during flight training, but that is most of the time that is our goal. So there's also some secondary effect with rudder, and it has to do with the speeds of the wings. So when you are yawing the glider to the right like this left wing will be moving a little faster than the average speed of the glider. This right wing will be moving a little slower. When the wing goes faster, it produces a little more lift, which tends to cause some degree of roll. So when you yaw to the right, the aircraft will tend to, with rudder, the aircraft will tend to roll to the right a little bit also. So at least in that case, the secondary effect is in the desired direction. So when we want to make a glider turn, how do we make that happen? This picture shows the lift vector and the weight vector when we're not turning, when the glider is in a is going straight. When we bank the glider, the weight vector continues to be downward, but the lift vector is now angled off diagonally. So it has a vertical and a horizontal component now, illustrated by these thin arrows. The horizontal component of that lift vector, that's what causes the aircraft to change direction and start moving. Its flight path gets diverted toward the right. If the lift vector stayed the same, then the vertical component of that lift vector would be smaller than the weight, and the aircraft wouldn't be sustained at the same. It would start to nose over and head toward the ground. So to avoid having that happen, we need to actually increase the magnitude of that lift vector in order to keep the magnitude of the vertical component equal to the weight of the aircraft. So in a turn, the wing has to produce more lift than what it needs to produce when we're going straight. Another thing we need to do while we're turning is we need to make sure that the direction that the aircraft is pointing keeps up with the direction that it's moving. So as we change our flight path and divert it to the right, we want the nose to come over. The vertical stabilizer helps to accomplish that, but we usually need to use rudder to supplement what the vertical stabilizer would do and force it over a little more. At a given airspeed, increasing your bank angle will increase your rate of turn and it'll decrease your turn radius. Also, at a given bank angle, increasing your airspeed will decrease your turn rate and increase your turn radius. So if you want to make a tighter turn, you've got two different choices. You can either choose a higher bank angle or you can choose a lower airspeed. Both of those things will tend to move you closer to a stall condition. So if you've got plenty of margin over stall, you can choose either of those options to tighten up a turn. If you don't have margin over the stall, then you need to make some choice other than tightening up the radius of your turn. Gliders usually will have some lift and drag modifying devices on the wings, which make it much more really help with controlling our glide path when we're coming into land. The surface on the bottom of the wing that sticks out the controllable surface, that's called a dive brake. The one on the top of the wing is called a spoiler. Some aircraft have both, some just have spoilers. You will hear the terms dive brake and spoiler kind of used interchangeably. If you're in one of a club's globes, which only has spoilers, you may still have a ground crew person remind you to close your dive brakes. He means close your spoilers. The spoilers and the dive brakes have the effect of reducing the lift over the section of the wing that they are deployed on, but they have a really big effect in increasing the amount of drag produced. So decreased lift, increased drag, both of those things will make the glider come down at a steeper angle. which you use them to control your angle of descent when you're trying to land. Flaps are another type of lift and drag modifying device on the wings. None of the club gliders have flaps, although there are gliders with flaps that you may encounter. The club tow planes have flaps, so you can see how you can look at those to see how flaps operate. Flaps, when deployed, they increase both lift and drag. Usually deploying them a little bit mostly increases the lift, and then further deployment mostly increases drag. But all of these devices tend to be used like for lower speed operation. Some gliders have flaps that can deflect in the opposite direction. They actually tip up at the back of the wing, and those are used at higher speed. There's a number of different types of flaps. The most common is this top picture, which is called a plane flap. Simply the last section of the wing is a separate piece, which is on a hinge and hinges at that point to deploy like this. A split flap is actually a separate piece that is on the bottom of the wing and moves, and creates this little gap here when it's deployed. A slotted flap is sort of similar to a plane flap, but there's an intentional gap when the flap is deployed, so that when the flap is deployed, air can go under the wing and still go over the flap. The effect of that is it increases the lift more than a plane flap with less of an increase in drag. This fourth picture is a Fowler flap. And this kind of a flap, the flap, in addition to changing its orientation, it actually moves fore and aft as it's deployed. So when it's not deployed, it'll be up here, and when it is deployed, it's making the wing effectively bigger with more area. So it has a higher amount of impact on the amount of lift by doing that. So trim is used to relieve the pilot of needing to hold constant pressure against the control stick. When you have to hold constant pressure against the control stick, you tend to be less accurate. You get tired after a while, and you tend to be less accurate controlling the aircraft. So it's good to manipulate the trim so that you're not holding constant pressure. And in typically the only axis that we worry about trim for is the pitch axis. I know of some airplanes that also have rudder trim, although even in airplanes that's not super common. But almost all airplanes and gliders will have pitch trim. There's a couple of different ways that trim is accomplished. The two Grobes that we have in the club actually illustrate both of the two. The one way is with something called an anti-servo tab. This is a tab. It's another little control surface at the back of the elevator. So the elevator is at the back of the horizontal stabilizer, and then the trim tab is at the back of the elevator. And the control surface, or the trim control, moves that surface with respect to the elevator. So if the trim tab is deflected down, there's an aerodynamic force created which tends to deflect the elevator up. The fact that those are opposite is why it's called an anti-servo tab. The other type of trim system that you'll encounter is a spring-based system where there's a spring which exerts some force on the control stick. And when you change the trim adjustment, you're basically changing the amount of force that that spring is exerting by changing the point that it's attached to. So that will be, you'll notice that even when the aircraft isn't moving. If a anti-servo tab only has effect when the aircraft is flying, but that's of course when you need it. So landing gear and brakes. This is a picture of our 233, which has very simple landing gear. So we have a single wheel located in the center of the aircraft near the center of gravity. The fact that there's only a single wheel means if the glider is not moving, the landing gear doesn't do anything to keep the wings level. So one wing will fall to the ground and you need to have a wing runner hold the wing in position when you're starting your ground roll. This has a nose skid which provides braking force. So when you want braking, you let the nose touch the ground and you get braking. It's of course very important when you don't want braking to make sure the nose isn't dragging along the ground. This is a picture of the DG505 at Sandhill, which has more complicated landing gear. So it has a main wheel like in the center, like the 233, but this wheel is retractable into the fuselage. So after takeoff, the pilot can pull the wheel up and then these doors close, and that makes for significantly less drag and better performance. It also is a thing that could potentially be forgotten when you're landing. This has a brake on the wheel itself, and a lot of gliders do. Our Grobes have brakes on the wheels. The brakes in some gliders, the brakes are controlled by a separate control. There's a and it isn't totally consistent from one glider to another. Sometimes it's like a trigger mechanism on the stick. Sometimes it's another lever. In the Grobes, the brake control and the spoiler control are integrated with each other so that the first bit of movement of that control deploys the spoilers, and then after the spoilers are completely deployed, additional movement of the control applies the brake. Like our Grobes, this has a nose wheel and a tail wheel. So if the nose touches or the tail touches while you're rolling along the ground, it isn't a big increase in the amount of drag slowing you down. Now motor gliders, we don't currently have one in the club, but you'll see them occasionally, especially when I'm out at the field. Motor gliders are designed to be operated without a wing runner. So their landing gear is a little bit different. In some motor gliders, they'll have a single main wheel, just like a regular glider, but they will have some wheels out on the wings that help keep the wings level without needing a wing runner. Other motor gliders have landing gear that's very similar to airplane landing gear. So when I'm out at the field with my Pipistrel, you'll notice that the landing gear looks a whole lot like the tow planes. Tow hooks. Both the both the tow plane and the glider have tow hooks. So it's releasable from either end. There are two different designs by different manufacturers for tow hooks, and you'll find both of them in the aircraft at Sandhill. So the Schweitzer design tow hook, it's got this bar here that pivots up at the front and is held in place by this latch at the back. And when you pull the release hook, the latch comes back and the tow rope pulls the pivoting arm out of the way and it comes loose. The Toast has two little claws that come together around the tow hook, and when you pull the release, that pulls them apart from each other so that they release. The 233 and the Bird Dog have the Schweitzer type, and the rest of the Pawnee and all of our other gliders have the Toast type. The tow ring, which attaches to the tow hook, is different in the two cases. So an important thing to know when you're the ground crew is you have to know the difference between a Schweitzer ring and a Toast ring, and you have to know which kind of tow hook you're hooking up to and make sure you've got the correct one. They're not interchangeable. Um, the exception is when we're using the golf cart to tow something around on the ground, we don't make a distinction between the two. But when we are hooking up to a tow plane, it's crucial to have the correct type. So a lot of times if you see the if the 233 is being operated on the same day that the other gliders are being operated, there's a extra piece of rope that gets attached to the tow rope, which converts it to having the Schweitzer ring. Another thing to know about tow hooks is that there's two different places on the glider that tow hooks may be located. Most of our gliders have nose-mounted tow hooks. The nose-mounted tow hooks work the best for aero tow when we're towing with a tow plane. Many of our gliders also have a CG hook that's located up under the glider near that main wheel. The CG hook is much better suited for launching with the winch. The Grobes have both kinds, so we have to use the correct one depending on which type of launch we're doing. The CG hook can be used for aero tow, although it's not as good. There's more opportunity for things to go badly and for a pilot to lose directional control of the glider during tow if you're using a CG tow hook. But it's allowed. You never use a nose hook for a winch launch. The Sometimes you'll encounter gliders that only have CG hooks, and they can be launched with either a winch or a tow plane. The 233 has a one hook which is kind of a halfway between the nose and the center of gravity and is usable for either, although not really great for either. So engines. Believe it or not, there are gliders with engines. In fact, the distinction between a glider and an airplane is not a sharp distinction. There's kind of a spectrum. On the one end, we have the pure gliders, like we're most of our club gliders that have no engine at all and always need a tow plane or a winch to launch them. A next level along the spectrum is gliders that have sustainer engines. The Discus that we have at the club is an example of a glider with a sustainer engine. That means that the engine is sufficient to help the glider climb if it gets low while out soaring. You can deploy the engine and use it to climb to a higher altitude to extend the soaring day and not have to land and get launched again. But a sustainer engine isn't sufficient to take off with, so you still need a tow plane or a winch. A self-launch glider, similar configuration to the sustainer setup, except the engine is a little more powerful and it's capable of taking off from a runway by itself without any tow plane and climbing. So that's more self-contained situation. Touring motor gliders are a lot closer to the airplane end of the spectrum. The engine is usually located up like in a location where an airplane engine would be, as opposed to being in a pod on top that you have to deploy. It is less the propeller doesn't retract, so the engine adds drag even when you're not using it. It isn't as capable as a glider as what a self-launched or a glider with sustainer is, but it is more capable of doing airplane type things. The landing gear is usually similar to airplane landing gear, so that it can be maneuvered around on the ground in an airplane kind of manner. So it's a lot like an airplane, except that it is, drag reduced and long, thin wings to make it capable of doing some soaring, but not as good as a pure glider generally.